In this video, we will be talking about gradients and directional derivatives. This is the overview slide, which I will go through first, and then we'll back up and go through each topic in more detail and with more examples. So our first topic is the directional derivative. So if f is a function from R3 to R, the directional derivative of f at x in the direction of a vector v, if it exists, is given by the derivative with respect to t of f of x plus tv evaluated at t equals 0. So let's look at this formula really quickly. This x plus tv you might recognize from chapter 1. This is the line that contains the point x and is in the direction v. T is what parameterizes and kind of extends your line out in the direction of v. So when we look at this, so we're at the point x, we want to be in the direction of v. So here is our line, x plus tv. So this is the line through x parallel to v. So the function that goes from t to f of x plus tv is the function of f that's restricted to the line x plus tv. So when we ask the question how fast of the values of f are changing along that line, along the line v at the point x, well, the answer is the derivative, the value of the derivative of the function at t equals 0. Which brings us to this theorem here. So if we have f go from R3 to R, if it's differentiable, then all directional derivatives exist. And the directional derivative at x in the direction of a vector v is given by the gradient of f of x dot v. And remember, the gradient symbolized by this del operator, del of f of x, are the partial derivatives of f with respect to, if it's R3, x, y, and z. So in other words, this grad f dot v is df dx evaluated at x dot v1, the first coordinate of the vector v, plus df dy evaluated at x dotted with the second coordinate, or multiplied, by the second coordinate of v, plus df dz evaluated at x multiplied by the third coordinate of v, and then these are all added together. If the gradient is not equal to 0, and actually what does that mean when the gradient is equal to 0? So that would mean all the partial derivatives in all the directions is equal to 0. In other words, it looks like it would, the df dx, so x must be a constant, y must be a constant, and z must be a constant, in which case there's no change. So if the function is changing, so if the grad of f of x is not 0, then grad of f of x points in the direction which f is increasing the fastest. So for example, if you have f of x, y, z equals x squared e to the minus yz, we can compute the rate of change of f at the point 1, 0, 0 in the direction of the unit vector v equals 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. And then we can also ask in what direction from 1, 0, 0 does f of x, y increase the fastest. So our gradient of f dotted with v. So df dx of x squared e to the minus yz plus df dy x squared e to the minus yz plus df dz x squared e to the minus yz dotted with v. So the derivative of this with respect to x would be our 2x, and then our e to the minus yz is just a constant. The derivative of this with respect to y, so x squared stays as a constant, and then you have to add a z component. So we have my minus x squared z e to the minus yz. And then the derivative with respect to z, again, our x squared is a constant, so we're going to bring down the y. So I have a minus x squared y e to the minus yz. And we need to dot it with v, which is our 1 square root of 3, 1 square root of 3, 1 square root of 3. And we're going to evaluate, where is that formula? Yeah, we need to evaluate our gradient at x, and x is equal to 1, 0, 0. So here we plug in 1, 0, 0. So the 0 here gives us e to the 0, which is 1, 2 times 1, so we get 2. And then here, because z is equal to 0, this will be 0 because y is 0, this is 0. So we have 2, 0, 0 dotted with our 1 square root of 3, 1 square root of 3, 1 square root of 3. So our final answer is 2 square root of 3. So that's the rate of change at this point, 1, 0, 0, in the direction of the unit vector. So if we're standing on a hill and we're at this coordinate, then if we wait, is that right? Yeah. And we travel in this direction, this is how fast we will be ascending. And the fastest change, so in what direction from, so if we're standing at 1, 0, 0, in what direction does f of x, y increase the fastest? And that's the gradient, which we had calculated here, evaluated at 1, 0, 0, because that's where we're standing. So when we plug in 1 here, we get a 2. We plug in 0 here. Is that true? We get a 1 times, oh, I'm missing a z here. So this should be 0, and this is also 0. So we get 2, 0, 0. Well, it's actually the same thing we had over here. Is that true? Yeah, it is. So we're going only in the I direction, in the x direction. So that's direction that things are changed fastest. Again, that's given to us by our gradient. So the gradient points in the direction which the values of f change the most rapidly. So the second point is, since the gradient points in the direction which the values of f change the most rapidly, whereas the level curves or level surfaces lie in the direction which they do not change, because remember, level curves, level surfaces, which we did earlier in this chapter, are when we hold the value of z constant. So if f changes the most rapidly, level surfaces do not change at all, then if f is reasonably well behaved, then the gradient and the level surfaces will be perpendicular, which gives us a way of computing a tangent plane of a level surface. If S is a level surface such that f of x, y, z equals k for k constant, then the tangent plane of S at a point x naught, y naught, z naught of S is defined by the equation gradient at your point, x naught, y naught, z naught, dot, and then x here is a random point on the plane. So since we're trying to find the equation of the plane, we're going to use a representative point x, y, z minus the point that we know is on the plane, x naught, y naught, z naught. So this is the line. When we dot it with our gradient, we should get equal to 0. This equation here will give us an equation of a plane. And of course, we're assuming that the gradient is not equal to 0. So for example, we can compute the equation of the plane tangent to the surface defined by 3xy plus z squared equals 4 at the point 1, 1, 1. So we look at our equation, 3xy plus z squared, and we'll take the gradient. So with respect to x, that'll be 3y. With respect to y, that'll be 3x. And with respect to z, that'll be 2z. We calculate the gradient at 1, 1, 1, and we get 3, 3, 2. So far we've done this part. And then we're going to dot it with x minus x naught, or x minus 1, y minus 1, and z minus 1, which we've done here. And this is the equation of our plane, 3x plus 3y plus 2z equals 8. The last thing we'll look at is the gradient of f as a vector field. So the thing about gradient of f, it assigns a vector to each point in the domain of f. So in other words, when we calculate the gradient, we get this df dx, df dy, df dz. So we plug in a point x, y, z, and we get back another triplet. We get the derivative of x, derivative of y, derivative of z. So in other words, we can't really graph the gradient of f because that would be R6, right? Because we plug in 3 dimensions and then we get out 3 dimensions. But we can represent the gradient for each point P as a factor, and that should be a vector, emanating from the point P rather than the origin. So in other words, here's our graph. So at point P1, P2, we'll just kind of plot it. Then we calculate the gradient at P2, and then we have whatever vector it is from the origin, and then we just move it up to P2, and that's how we represent the vector field. So The gradient vector field shows the direction that it is increasing fastest and orthogonal to the level surfaces. And we have this one last example. Find the unit vector normal to the surface given by z equals x squared y squared plus y plus 1 at the point 0, 0, 1. So here's our f. And we rewrote this as f of x, y, z as x squared y squared plus y plus 1 minus z. The gradient of f, derivative with respect to x, is 2xy squared. Gradient of y is 2x squared y, and the gradient of z is -1, evaluated at 0, 0, 1 is 0, 0, 1. And then the vector perpendicular to s at 0, 0, 1 is the unit normal vector, 0, 1, -1. That was our overview, so now we can go through each topic in more detail and with more examples. Our first concept is of the directional derivative. So if we have f going from R3, so xyz, into a scalar r, the directional derivative of f at a point x in the direction of a vector v, if it exists, is given by this formula d dt f of x plus tv evaluated at t equals 0. So first, let's just look at this x plus tv. This is actually the parameterization of a line that goes through the point x, and it's a line in the direction of the vector v. This is something we had covered earlier, so just in case you have forgotten, we'll review that. So the parametric equation of a line passing through the endpoint of a vector A, so I want my line to pass through A, let's just say A is 2, 1, in the direction of a vector V, so I want it in this direction, let's just say my vector direction I want is 1, 3, so I want it to look like this. And it's given, parameterized by this equation, L of t equals A plus TV, where t is a scalar that we multiplied by. To see that this is going to give us this line, well, when t is equal to 0, we just get the point A, so we have this point here. Maybe I should do this in blue. Now, when we have, for example, t is equal to 1, we're going to move this vector here, and we'll get this point here. So again, this point came when we let t equals 1. What if we let t equal 1/2? So we'll only have, I guess I need a different color, this much of the vector now, half of the vector. When we add it, we're going to get this point here. So you see, if we then double the vector, we'll get some point out here. And if we do negative times the vector, we'll get points back here. And when we just let t vary, you can see that we're going to get this line through the point A in the direction of V. Again, this is what we covered in chapter 1, probably the first video that we went through. So in this example, A is our point on the line here. Up here in this statement, we're talking about x being the point on the line. So maybe I can erase this x and put A. I didn't actually put A because x is, the name of the axis, but whatever. So here we have x, line through the point x in the direction of v. That's exactly what this is. So x plus tv is the line through x parallel to the vector v. So the function that goes from t to f of x plus tv, this part here, so you're plugging in, so just to be clear, x is given, v is given, so t is your variable. So here, f of x plus tv is essentially the function f restricted to the line x plus tv, because you're plugging in t, values for t, so you're plugging in, the output is going to be points on this line. Okay, and the question is now, how fast are the values of f are changing along the line at the point x? And the answer would be the derivative. That's how fast they're changing. And then, so the answer is the derivative at t equals 0, because you want it to be at this point, right? You don't want it to be at one of the other points, so at t equals 0. So this is the idea of the directional derivative. If we're looking at x, we want to know how fast we're changing in this direction v. So now we have this theorem to help us out. So if f goes from R3 to R, if it's differentiable, then all the directional derivatives exist because that's what it means to be differentiable. And the directional derivative at x in the direction of v is given by, and what we have is the gradient. We have these three different notations for gradient, df and v, or grad f of x dot v, and this is the one I tend to use, the del f of x dot v. And what that is, remember the del operator is the partial derivatives of f with respect to its three variables x, y, and z. So in other words, the gradient of f is df dx, df dy, and df dz, or partial with respect to x, partial with respect to y, partial with respect to z. And we're going to dot that with v, so we're going to get df dx evaluated at x dot multiplied by v1 plus df dy at x multiplied by v2 plus df dz evaluated at x multiplied by v3. And this is the shorthand formula, del of f dot v. And then we have this other important theorem. So if the gradient does not equal 0, so we will see an example what we can say about this when it does equal 0. But if the gradient of f of x does not equal 0, then the gradient points in the direction along which f is increasing the fastest. We have our example of this theorem. Let's say f of x, y, z is equal to x squared e to the minus yz. We want to compute the rate of change of f at the point 1, 0, 0 in the direction of the unit vector v equals 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. In other words, it's the 1, 1, 1 vector normalized. And the answer is the gradient of f dotted with v. So the gradient of f is df dx of our function, df dy of our function, df dz of our function, dotted with v. The derivative, partial derivative with respect to x will be our 2x times e to the minus yz. Derivative with respect to y, x squared is a constant, so we just bring down the z, so we have minus x squared z e to the minus yz. Derivative with respect to z, now we have y is a constant, so we bring down the minus y times x squared e to the minus yz, and then we dot it with v. And one other thing here in my formula up here, I do have to evaluate df dx at my point x. Actually, so yeah, this x is this point x. It's not the df dx x, which is why maybe this should have been a, but this is what's in your textbook, so I use this here. So I need to evaluate it at my point x, which is 1, 0, 0. So I just put that here, which actually gets plugged into here. You know, no x's, y's, and z's in here. And my final answer will be 2 over square root of 3. And again, this is the rate of change of f at this point in this direction. So in other words, again, if you're at some hill and you're at this location and you're facing this direction, then the rate of change, like of the height, how high, how fast the descent is at this point in this direction, is given by this number 2 over square root of 3, and we don't have any units, I guess, because it's a math class. And again, this is sort of a measure of how steep this point is in this direction, if you're looking in this direction at this point. Now, if you want to know, and you're standing at this point, 1, 0, 0, and you want to know what direction to go that your climb will be the fastest, so now we're not looking in this direction, we want to know what direction do we need to face such that the hill is the steepest. In other words, f of x, y, z increases the fastest. We can also then take the gradient and plug in our point. And the answer to this is the fastest change. In other words, where f of x, y, z increases the fastest is the gradient, which we had calculated here, 2x e to the minus yz minus x squared e to the minus yz and minus x squared y e to the minus yz. And the gradient at this point that we're standing at, 1, 0, 0, because of course, if you're on a hill, how fast it can go, be steep, depends on where you're standing, so you have to give it a point. So when I plug in 1, 0, 0, I plug in 1 here and I get 2 times 1, And then my 0 here just gives me 1. So I have 2 so far. Here, because y is 0, this becomes 0. Because z is 0, this becomes 0. So I have 2 in the x direction, or in the I direction. So the direction, the 2 is just the magnitude. So the direction of fastest change is the I direction, or the 1, 0, 0 direction. Since the gradient points in the direction in which the values of f changes the most rapidly, whereas the level surfaces lie in the direction in which they do not change at all. Remember, level surfaces and curves are when we hold our function equal to a constant. In other words, it doesn't change. Then if f is reasonably well behaved, the gradient and the level surface will be perpendicular to each other. This fact will give us a way of calculating the tangent plane of a level surface. So let S be the surface, such as f of x, y, z is equal to k for k constant. Then the tangent plane of S at a point x naught, y naught, z naught of S is defined by the equation. The gradient of f at x naught, y naught, z naught at the point, dotted with x minus x naught, y minus y naught, and z minus z naught. And this x, y, and z, that's a representative point on the plane. So x minus x naught, y naught, z naught is the line between, or the vector between, it's actually from x naught, y naught, z naught to the random point x, y, z. So any point x, y, z that satisfies this equation is a point on the plane. But here is the equation then that gives you the plane. I moved some things up and deleted some things, so just to give us some more space so we can do this example. So we want to compute the equation of a plane tangent to the surface defined by 3xy plus z squared equals 4 at the point 1, 1, 1. So using this formula here, actually this is going to be pretty quick. First we need the del, the gradient of f. So taking the derivative with respect to x, we get 3y. The derivative with respect to y, we get 3x. And the derivative with respect to z, we get 2z. We evaluate that at 1, 1, 1, which means that at this point, this will give us, okay, so the gradient gives us where things are changing, the direction of fastest change. And at this point, 1, 1, 1, the direction of fastest change is 3, 3, 2. Now, we want the equation of the tangent plane, though. So I'm going to take this del of f evaluated at x naught, y naught, z naught. So that's that 3, 3, 2, dotted with x minus x naught, y minus y naught, z minus z naught. So that's x minus 1, y minus 1, and z minus 1. Doing the dot product, 3x minus 3, 3y minus 3, 2z minus 2, will give us 3x plus 3y plus 2z is equal to 8. So this is the equation of the plane tangent to the surface defined by this 3xy plus y squared equals 4 at the point 1, 1, 1. We are at our last concept, which is the gradient of f is a vector field. So I cleared things out, moved it up. So the gradient of f is a vector field. So the idea of the gradient, it assigns a vector to each point in the domain of f. So we don't graph the gradient of f per se because that would be an R6. That would be x, which is our three-dimensional point, and the gradient of f is another vector. But we represent the grad of f for each point P as a vector emanating from the point P rather than the origin. This is probably illustrated best with an example. So the example is to find the unit vector normal to the surface as given by this surface here, z equals x squared, y squared plus y plus 1 at the point 0, 0, 1. So we're going to work this problem, but first we're just going to look at what this vector field looks like. I'm going to use this function, so I have z equals x squared plus y plus 1. I move my z over, so I have 0 equals x squared plus y plus 1 minus z. I could have put the 1 over here. But now this is my function f. My gradient of f is this with derivative with respect to x, which is 2x, derivative with respect to y, which is 2y plus 1, derivative with respect to z is negative 1. So now I can plot x, y, z versus gradient of f. So if I'm at 0.000, my gradient of f is going to be 0, 1, negative 1. If I'm at my 0.111, my gradient is going to be 1, 3, negative 1. I'm sorry, 2, 3, negative 1. And if I'm at the 0.010, I'm going to be at 0, 3, minus 1. So this is what I mean by here, we're in R6 if we're plotting x times gradient of f, because x is a three-dimensional and gradient of f is three-dimensional. So we're not going to make a six-dimensional graph, but we'll do this in 3 dimensions. So at 0.00, I have the gradient is equal to 0 along the x-axis, 1 on the y, and then negative 1 along the z. So this is my gradient vector, and I anchor it at 0, 0, 0. Now, when I look at this point 2, 3, minus 1, so I'm over here 2 on the x, 3 on the y, and at minus 1. So this is my point. So my vector 2, 3, minus 1 looks like this, which unfortunately looks a lot like negative 2.5 or something in the z direction, but that's not what it is. But the way we are going to represent this now, I guess it's over here, we're going to move this vector at the point 1, 1, 1, which is like 1 on the x-axis, 1 on the y, somewhere around here. So I'm going to move this vector. Let me try this again. Move this vector so that its point is at 1, 1, 1. And then I can get rid of these squares. Doesn't look that impressive, but you know, at least you saw how I got that. Now, if I look at the point 0, 3, minus 1, so I'm at 0 on the x, 3 on the y, and then minus 1. So my vector is going to look something like this. And then, again, it's according to this direction. You know, we represent the gradient as a vector emanating from the point P rather than the origin. So now I'm going to move this at the point 0, 1, 0. And that's 0, 1, 0. So it's at this point here. So I'm going to move this vector here. So that's what my gradient field looks like. So what that tells me is at this point, 0, 0, 0, this is the direction of fastest increase for my function. If I'm at this point here, which is theoretically 1, 1, 1, then this is the direction of my fastest increase. And if I'm at the point 0, 1, 0, this is the direction of fastest increase. We haven't really talked about vector fields, and we will more in Chapter 3. But the basic idea of a vector field is that it's a function that assigns to each point a vector. In this case, our gradient is a vector, gives us a vector field because it assigns to each point, each x, y, z point, a vector. I also just realized I copied this function incorrectly here. So we're just going to go with it because I don't want to redo this example again. Now we can go back to our original question. Find the unit vector normal to the surface given by this at the point 0, 0, 1. So the idea is the unit vector normal to the surface. So that will be the vector. So the surface, if we had a level curve or level surface, that would be where there's no change, and then the gradient will give us the perpendicular. So we have our function f of x, y, z, and I rewrote this again as x squared y squared plus y plus 1 minus z. So the gradient now, derivative with respect to x, which is 2xy squared, derivative with respect to y, which is also 2x squared y plus 1, I guess it's not also, but 2x squared y plus 1, and derivative with respect to z is equal to negative 1. So this gives us, this gradient tells us the direction of fastest ascent, or the place where the function is increasing the fastest. And of course it's different at every point. So when we plug in 0, 0, 1, then we have the direction 0, 1, negative 1. So if we're on this hill and we want to know which part is steepest, of course which part is steepest depends on where we're standing, but if we're standing at 0, 0, 1, then the direction of 0, 1, -1 will give us our fastest ascent. So the vector perpendicular to the surface at 0, 0, 1 is the unit normal vector. So here, because it asked for a unit vector, we're going to normalize it, and we get 1 over square root of 2, 0, 1, -1. Now that we've covered our main topics, we'll do some more problems. For our first example, we're going to consider the surface z to the fourth equals x squared plus y squared. Now, because I want to take the gradient and consider level surfaces, I'm going to move the z over, so my f of x, y, z is equal to x squared plus y squared plus z. So here's our function. I have it over here, and what we are going to see, and so this isn't so much a question, but I'm going to illustrate that at this point, we're going to have a hard time looking at the gradient at 0. And you might already kind of see why. Then I can take my gradient of f here, derivative with respect to x, derivative with respect to y, derivative with respect to z, and I evaluate it at 0, 0, 0. And I see that that's equal to 0, which is unusable. Remember, our theorems talk about the gradient not equal to 0. So it's unusable for a normal for a tangent plane. And if you look at the graph of this function, you can kind of get a sense of why that is the case. In this next example, we're going to determine the tangent plane to the paraboloid given by the equation z equals x squared plus 3y squared at the point -2, 1, 7. And for this example, we're going to do it two ways. The first way is we're going to consider this a surface. So in other words, we're going to say z is our surface given by the equation x squared plus 3y squared. And then we're going to look for the tangent plane using the equation we had from the chapter when we talked about derivatives and tangent plane. And this is the equation we had, which is we start with f of x naught y naught, and then we take the partial derivative with respect to x, evaluate it at x naught y naught, and multiply it times x minus x naught, plus df dy x evaluated at x naught y naught times y minus y naught. So again, this is the equation for a tangent plane to a surface that we learned when we talked about derivatives. So the idea is now we can view this z as a surface given to us by the equation x squared plus 3y squared. The second way we're going to do this is to move the z over and consider this now a function where we have the level surface at c equals 0, or height z equals 0. So this now is a level surface of this function x squared plus 3y squared minus z. It's a level surface with c equal to 0. And then we're going to use the tangent plane equation we learned in this video, where we said, well, if it's a level surface, it's going to be perpendicular to our gradient. So we're going to take the gradient of this function, input our point x naught, y naught, z naught, which is our -2, 1, 7, and then dot it with x minus x naught, y minus y naught, z minus z naught, and set that equal to 0. So there are two ways of getting this tangent plane. And again, the first one comes from using our definition of derivative, the tangent plane from using definition of derivative. The second one is from viewing this now as a level surface and then using the fact that level surfaces are perpendicular to the gradient. So this first level, actually both of these go really fast. This first way of doing this, we need f of x naught, y naught. So f of x and y is f of -2, 1, which is giving us 7. And then our partial derivative with respect to x, partial derivative with respect to y. So I just take the gradient of f. So that's going to give me, well, here's f, 2x and 6y. I evaluate that at -2, 1, and I get -4 and 6. So that'll give me df of x evaluated at x naught, y naught, and df dy evaluated at x naught, y naught. So now I just need to plug in. So I have my f of x naught, y naught, which is 7, df dx evaluated at x naught, y naught, which is equal to -4 times x minus x naught. So that's x plus 2, plus df dy evaluated at x naught, y naught, which is 6. I keep wanting to point to the gradient evaluated at 1, this 2, 1, but it's over here. 6 times y minus y naught, and y naught is equal to 1. So this is our equation, which I simplified to 4x plus 6y minus 7. The second way we do this is using our tangent plane equation, using the fact that the gradient is perpendicular to the level surface. So first I'm going to take the gradient, which again is the same thing, except, oh, actually now this is my function. Sorry, it's not the same thing. So it's 2x, 6y, and minus 1. And then the gradient evaluated at 2, 1, 7 is going to give me my negative 4, 6, negative 1. So now I can dot my gradient at my x naught, y naught, z naught, which is 4, 6, negative 1, dotted with x minus x naught, which is x minus negative 2, which is x plus 2, y minus y naught, which is y minus 1, and z minus z naught, which is z minus 7. I dot this, and I do some algebra, and I get minus 4x plus 6y plus z equals 7, or minus 7. And these are the same equation, I just moved the z over, and I have the same equation. So two different ways of coming up with the tangent plane here. The first one, just using the fact, viewing this z as a surface, and then looking for the tangent of the surface, using this derivatives, the partial derivatives, or moving this over, z, and now saying that this is my equation of some graph, and that I'm looking at a level surface and using the fact that the gradient is perpendicular to the level surface. Now we've finished all the material for this video, so we'll review that. First we talked about directional derivative, and so if we have a function from R3 to R, the directional derivative of f at x in the direction of a vector v, if it exists, is given by df of x plus tv, and remember this is the line through x in the direction of v, the derivative at t equals 0. And the idea is this is the line through x parallel to v. So this function, remember this is a function of t because x is given and v is given, t is your variable. So this function goes from t and it's restricted on the line x plus tv, right? You have x, you have v, it's given. It's just, these are just points on the line. So if you want to know how fast the values of f is changing along the line, you take the derivative. And if you want it at the point x, you need to set t equal to 0. And then we kind of defined in general what a directional derivative is. So if R3 goes to R, if it's differentiable, then all directional derivatives exist, and the directional derivative at x in the direction of v is given by the gradient of f dot v. And we had this theorem. If the gradient is not 0, then the gradient of f points in the direction which f increases the fastest. And we have this example where f of x, y, z is equal to x squared e to the minus yz. We can compute the rate of change of f at 1, 0, 0 in the direction of the unit vector v, 1, 1, 1 normalized. And we can also answer at this point what in what direction does f increase the fastest. So first, we're going to take the gradient of f, which is, where is the gradient of f? It's right here. So partial derivative of this with respect to x is 2x e to the minus yz. Partial derivative with respect to y, that just brings down the z, so you get x squared z e to the minus yz. Partial derivative with respect to z just brings down the y here, so you get minus x squared y e to the minus yz. This is our gradient that tells us the rate of change, the fastest rate of change. And the rate of change really depends on where you're standing, right? If you're on a hill, how fast the hill becomes steep or doesn't become steep depends on where you're standing. So if you're standing at 1, 0, 0, you can plug that in. And of course, also how fast it's changing depends on which direction you're going. So we can also use, we need to dot that with our vector. So this is the answer to the first question. You plug in 1, 0, 0, dot it with the vector, and your answer is 2 square root of 3. And in general, what direction, when you plug in 1, 0, 0, does f of x, y, z increase the fastest? You just plug in 1, 0, 0, and we see that the direction is the I direction. This next theorem, since the gradient points in the direction which values of f change the most rapidly, whereas the level surface lies in the direction which they do not change at all, if f is reasonably well behaved, the gradient and level surface will be perpendicular. So we have the second way of computing a tangent plane. So this is tangent plane of a level surface. So if S is a surface and we set it equal to a constant, so it's a level, this is a level surface, then the tangent plane of S at a point x naught, y naught, z naught can be defined by the equation. We take the gradient at that point, we dot it with the level, a line on the level surface, and since this is a level surface, it's perpendicular to the gradient, so it should equal to 0. And we have this example. We have this level surface defined by 3xy plus z squared equals 4 at 1, 1, 1. So 4 is our constant for our level surface. We can take the gradient. So we have this with respect to x is 3y, with respect to y it's 3x, and with respect to z it's 2z. Evaluated at 1, 1, 1 gives us 3, 3, 2. So this is the direction. If we're at the point 1, 1, 1, this is the direction we should go, and that'll give us our steepest ascent. So the tangent plane now is this gradient dotted with x minus 1, y minus 1, and z minus 1. And then this is our final equation. Last we talked about gradient of f being a vector field. So the gradient of f assigns a vector to each point. We don't graph the gradient of f per se, or because that would be an R6, but we can represent the graph by, for each point P, we compute the gradient, and then we move the vector that we get for the gradient from the origin to the point P. And we did an example of that, and this other example we did as well. For a review, I have these two problems for you to try, so pause the video, give them a try, and when you come back, I'll have solutions. These are the two solutions. And that is it for this video. Thank you for watching.